confidence intervals for population proportions. Our objective: construct and interpret a confidence interval for the population proportion. All right, let's begin by discussing what we already know coming in. We know that the shape of a sampling distribution of P, the population proportion, is approximately normal provided n times P times 1 minus P is greater than or equal to 10, and provided the sample size is no more than 5% of the population size. Sample size is lowercase n, less than or equal to 0.05, 5%. Population size, uppercase N. This second one is pretty much always met, but we're going to include that and make sure that we're good. But it's pretty much a guarantee that this is not an issue. The first one is the one that we want to be more focused on, although we'll deal with both. We know what a point estimate is: the value of a statistic that estimates the value of a parameter. And we know that when we're speaking about data using proportions, we're working with qualitative data that has two possible outcomes. Generally, agree, disagree, or yes, no are the kinds of things we're working with here with proportions. Okay, so let's go through a little bit about some vocabulary and some sense of what we're doing here. All right. Samples, of course, are used to estimate population proportions. It is essentially certain you're never going to be exactly correct. You're never going to have the sample proportion is never going to be exactly the same as the population proportion. Okay, yeah, you may get really, really lucky, but it's kind of like winning a big lottery. All right. And of course, our statistics vary from sample to sample. So to account for this never being exactly correct, we build an interval around our point estimate. So we're going to say, well, I think it's this, but I'm within this or this. Okay, you're going to try to build an interval around it to give people an idea of how much variation or what you expect there to be for a little bit, how much error you may have included. So we build a confidence interval centered around our point estimate, an interval of numbers that is based on the point estimate. Okay? The level of confidence. How confident do we want to be? The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. All right, common levels of confidence. We want to be 90% confident, 95% confident, or perhaps 99% confident. How confident do you want me to be that my interval contains the proportion that relates to the population? For example, and here's how you talk about it. A 95% level of confidence implies that if 100 different confidence intervals are constructed, each interval based on a different sample of the same size from the same population, then we expect, there's no guarantee in statistics, we expect 95 of the intervals to include the parameter and 5 of the intervals to not include the parameter. We expect that to happen. You may have 96 intervals that include the parameter. We don't know. But if we're 95% confident, we expect that if we do 100 of these, there will be 95 that include the parameter and 5 that do not. It is an expectation. It is not a guarantee. Okay, let's flip it over and take a look at how this works with the confidence interval and level of confidence. All right, get straightened out here. In statistics, we construct an interval for a population proportion based on a statistic from the sample, along with a level of confidence. The sample proportion is the point estimate, and the level of confidence determines the width of our interval. So here is our point estimate, our guess, based upon the sample. If we want to have a low level of confidence, 90% confident that it's in here, we have a smaller interval. Okay? The higher the confidence the higher the confidence, the larger the interval that we want to have to make sure we're correct. So I'm 90% confident it's in this small interval, but I'm 99% confident it's in this slightly larger interval because I have expanded, I've widened the interval, I can up my level of confidence. Okay? Confidence interval estimates for a population proportion are of the form, the point estimate plus or minus the margin of error. All right, well, that introduced another term for us. What is margin of error? The margin of error is the upper bound of the confidence interval, up here, minus the lower bound of the confidence interval, down here, divided by 2. So you take the confidence interval, it's half of, this is your width, it's half of that width. And it is the margin of error of a confidence interval estimate of a parameter is a measure of how accurate the point estimate is. Margin of error depends on your level of confidence. As the level of confidence increases, a lower level of confidence, as your level of confidence increases, your margin of error also increases. You're going to have a greater chance, you're going to have a larger margin of error for a high level of confidence. Also depends on your sample size. If your sample size increases, your margin of error decreases. That makes sense. More and more people included in the survey, your margin of error is going to go down because you're including more and more people, okay? And it also depends upon the standard deviation of the population. Let's talk about what it says. Given repeated sampling, let's talk about a repeated sampling interpretation of a confidence interval. What it says, a 95% confidence interval indicates that 95% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the true value of the parameter. Okay, note, and this catches people, a 95% confidence interval does not mean there's a 95% probability that the given interval contains the true value. That's not what it means, right? It means that 95% of all samples will result in an interval that contains it. It doesn't mean there's a 95% chance that your particular interval contains it. Does not mean that. This will be greatly assisted by a couple of examples. So let's do that. Give me a moment here to get my act together. And we'll take a look at a couple of examples. It'll make a whole lot more sense once we've done that. Okay, example number 1. And we're going to use StatCrunch to do our confidence intervals for us. So letter A here, algebraically calculate the point estimate for the population proportion given that the number of successes X is 80 and the sample size is 200. Okay, so A, we're estimating the population proportion. Our estimate is the sample proportion, which is P hat. This is the sample proportion that we are using to, I gotta spell proportion correctly. P-R-O-P-O-R. Okay, we're using this to estimate our population proportion, and it's X over N. So it is 80 divided by 200. That goes into a calculator, and up comes 0.4. So our sample says that the number of successes is 0.4. As a percent, 40%, but we're going to keep it as a decimal 0.4. Okay, now we're going to use StatCrunch to build an interval around 0.4 that will show us an interval that will indicate we have a 98% confidence that we have contained. We don't know what the true value of the population success rate is. Our sample says it's 0.4, but it could be 0.39, it could be 0.42. We don't know. We've only done a sample. So we're going to go to StatCrunch, the proportion stats calculator, to construct a 98% confidence interval to 3 places. Okay, so here we go. Into StatCrunch. Let me move this out of the way. Okay, and let's get StatCrunch to maybe get ourselves, we get into where we're, let's go down to here. I think that's pretty, let's get my hand out of there. Let's get it focused. Get focused. I think we're focused. Okay, let's take a look. So we're going to go into stat, proportion stats, because we're dealing with proportions. And this is from a single sample. And our data has already been put together. We already know that 80 out of 200, so the data is not raw. The data has been summarized with summary. Okay, we get this table right here, and we put in number of successes. Well, we had 80 successes. 80 people said, for example, yes. Out of observations, well, the total number in our sample was 200. We'll put 200 in there. Okay, we want to perform a confidence interval for P. We're not looking to perform a hypothesis test. We need to select the confidence interval for P. And our level, we say we want 98% confidence. Well, 98% as a decimal is 0.98. So I'll go to there and put in 0.98. I don't change anything else, and I'll press compute, excuse me. I'll press compute. There we go. Okay, notice, this is our 98% confidence interval. We had 80, we were 80 successes out of 200. It calculated a sample proportion for us. We did it by hand, but here it is, 0.4. The lower limit of our interval is 0.319. I'll make it 0.32. The upper limit is 0.48. Okay, so we just came up with our interval. Our interval goes from 0.32 to 0.48. Let's note that. The calculator did it for us. So let's note that here. Okay, so letter B. Our lower limit, we said, was 0.32. And our upper limit of our confidence interval, we calculated as 0.48. Okay, so what are we going to say here? Let's interpret our results. We are 98% confident that the population proportion, which we do not know, we know our sample proportion was 0.4. We do not know the population proportion, but we are 98% confident that the population proportion is somewhere between 0.32 and 0.48 based upon our sample data. Okay, so we're giving you a point estimate, 0.4, and then we're putting an interval around it. We've gone down by 0.08 and up by 0.08, and we're saying, okay, my sample said that the proportion of successes was 0.4. I want to be 98% confident that that is true. Okay, so I want to be 98% confident in what I think it is. Well, I'm 98% confident that that my population proportion, the number of people in the population who said yes, for example, will be between 0.32 and 0.48. The proportion will be between 0.32 and 0.48. Let's do one more example. maybe get in a bit more. I need to, let me go into here. Okay, I'm just checking my computer. Let's do one that's got some more of a real life application to it. Here we go. Okay, in July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. So the success in favor says they, obviously the success rate here, what we call success, is they were in favor of the death penalty for persons committing murder. Okay, letter A, algebraically obtain a point estimate for the population proportion of registered voters who are in favor of the death penalty for persons convicted of murder. Okay, letter A. P hat, that is our sample proportion, which is estimating. It is the point estimate for our population proportion. P hat is X over N. Well, the ones in favor, 1,123. The total sample size, 1,783. That goes into a calculator, and as a proportion, I rounded to 3 decimal places. It goes 9, 8, something, 0.630. As a percent, we could write that down. We would say 63% of our sample says they're in favor, and that is our point estimate for our population. Okay, but we don't know. Okay, this is based upon a sample. So we're going to construct an interval around it to say that we're a certain percentage certain that it's between this number and this number. After checking the sample size is large enough to be approximately normal, because we're not told it's approximately normal, we need to check that. We're going to use StatCrunch to obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty, and we're going to interpret these results. So let's check our sample size. And this goes back to the very beginning with what we already know. Okay, we got 2 things to check. Number 1 is N P hat times 1 minus P hat greater than or equal to 10. Well, let's see here. Our sample size is 1783. Our P hat is 0.63. And we have 1 minus P hat, and that comes out to be 415.6. Is that number larger than or equal to 10? Well, yeah. Way larger than 10. So that's our first check for normality. Our second check says, and this is the one that's usually just fine, but our second check says, is our sample size N less than 5% of the population? Well, our sample size is 1,783. Okay, I don't have any idea how many registered voters we have in this country. There are about 330 million people. Let's say 200 million. Okay, so I guess 200 million is a low ball. So is that less than 5% of 200 million? So here's 200 million, and you can do that math, but yes, our sample is way less than 5% of the population of registered voters. That's just fine. And again, number 2 here is almost always just fine, but we're going to do a check anyways with it. So we can move forward. We know we are approximately normal. We can move forward and pretend and work with it being normal. Okay, we can move forward. So let's go to our StatCrunch. And let's create this interval using StatCrunch. So, okay, I left mine up here. If you want, I'll go back. I'll close this. I'll go back to here. I'll go through the process again. We're going to go to Stat. We're going to choose proportion stats. There's proportion stats right there. We're doing a proportion. This data has already been summarized. It isn't raw. We already know how many said yes, and we already know the total number. So with summary, and we get to this box, number of successes. Well, our number of successes was 1,123. Okay. Now, how many observations were there? Well, we asked 1,783. Hope I got that right. People. Okay, we're going to go down to here. We're going to select the confidence interval. We're not doing hypothesis tests. We're doing confidence intervals. And we want a 90% confidence interval. So we'll go to, I had a 5 in there. We'll go back, put a 90 in there. Once we've done that, we'll leave the standard wall method or whatever method, and we'll press compute. Okay, so here's our sample proportion. 0.6298. Remember, I rounded that to 3 decimal places, 0.630. And here's our lower limit. I'll make a note of that, 0.611. And our upper limit is 0.649. 0.649. So we found our lower limit and our upper limit. Let's go back to our paper and answer the question. Okay, the question says, after checking it, we checked it. Obtain a 90% confidence interval. We did that. Okay, lower limit of our confidence interval is equal to 0.611. The upper limit is equal to 0.649. Okay. All right, so there's our interval between 611 and 649. So we are 90% confident that the true proportion of the population of all registered voters, we're 90% confident that the true proportion of the population of registered voters is between 0.611 and 0.649. Let's write that down. Okay, we're interpreting this. We are 90% confident that the population proportion, which is the proportion of registered voters, we're talking about all of them here, of registered voters in favor of the death penalty for those convicted of murder. Whoops, got ahead of myself with my writing. For those convicted of murder is between 0.611 and 0.649. Okay, so again, a brief recap on this one. We constructed a 90% confidence interval around our point estimate. And we're saying, okay, here's what we know. I am 90% confident that the population proportion, the proportion of all registered voters, is somewhere between 0.611 and 0.649. That's my 90% confidence interval. So there you have it. Confidence intervals for population proportions.